Well, thanks for having me. Sorry for the hiccup. So yeah, I'm Laurent. I'm from the open source security team at Google. And since this is the KLEE workshop, I want to talk about our efforts to integrate KLEE in FuzzBench. So what's FuzzBench? So as you may know, we use a lot of fuzzing at Google. We fuzz not just internal software, but we also fuzz open source software via a project called OSS Fuzz. And we see a lot of interesting fuzzing techniques being published, both in industry and academia. And most of the time, we'd like to integrate some of those techniques in our fuzzing pipeline. But it takes effort and it takes time to re-implement those techniques or port existing code. So we needed a way to understand which techniques are most promising so that we can prioritize our efforts. So unfortunately, most papers, and at least until maybe 2 years ago, did not follow a common evaluation process. For example, some papers do not use the same programs to test their techniques, or they may use different configuration for fuzzing. For example, they might enable seeds, or they might disable dictionaries for fuzzers. There's a whole bunch of configuration that can differ between papers. Coverage measurement is not standard either. Some papers will use lines as a coverage metrics. Other papers will use basic blocks or edges reported by fuzzers. And that's kind of the idea of why we started working on FuzzBench. In a nutshell, FuzzBench is an open source fuzzing benchmarking platform and service with a focus on real world programs. Today, we have around 20 programs that we integrated into FuzzBench, taken from a real world data set from OSS Fuzz. So FuzzBench takes care of many of the things that you have to do to run your experiments smoothly. It will run fuzzers for you, extract coverage, deduplicate bugs, plot results, and so on and so forth. And we believe that FuzzBench can speed up the time it takes for researchers to try out new ideas. FuzzBench complements other benchmarking programs that are smaller in size, for example, those that you find in Core Util. So we really see FuzzBench as a complement to those micro benchmarks. So what we did for KLEE is we integrated KLEE for 10 benchmarks out of the 20 available benchmarks we had in FuzzBench. I'll get back to this in a minute. In FuzzBench, a typical fuzzer integration takes around 100 lines of Python code. KLEE integration took a little bit more because we added code to monitor resource consumption at runtime and to help us debug. We also patched KLEE to generate binary inputs or outputs instead of the regular k-test files. This helps us take all the corpus that is generated and replay it into a measurer to extract coverage measurement. So before talking about the experiment that we ran, I want to mention some of the problems that we encountered along the way. I don't think this is unique to us, but I still want to point it out. So the first problem we encountered was around unsupported instructions, such as vectorized instruction or floating points. For example, we could not integrate KLEE for the Vorbis target because of this problem. We also encountered problem with long jump instructions and the use of assembly instructions. Unfortunately, many of those programs in OSS Fuzz make use of assembly instructions. I believe about half of them. And so a workaround would be to manually go into each of those programs, disable the use of assembly instructions. But unfortunately, there's no standard way to do this across all the programs. So this approach, even though it works on a small set of programs, doesn't really scale if you want to launch KLEE on hundreds or even thousands of programs. Another problem we encountered was the use of multi-threaded programs and system-level linking. Many programs in FuzzBench, in OSS Fuzz link against libraries that are installed on the system, such as OpenSSL or zlib and whatnot. So we need a way to understand all those dependencies and recompile them to generate the final BC file. or KLEE might just fail at runtime because it cannot find the the function that is called. It's possible to just run KLEE anyway, even if you don't recompile those dependencies. But as I said, KLEE might fail, and if it doesn't fail, it will concretize the value, which is not really ideal when doing symbolic execution. Yet another little problem we faced was out-of-memory issues. So KLEE would simply keep crashing, and even when we try to limit its memory usage via command line arguments. So what we did in the end is we ended up adding more RAM to the system, and that just fixed the problem. Okay, so now let's talk about the experiment that we ran and some of the results that we have. The first experiment that we ran was KLEE versus AFL++. I don't know if many of you know about AFL++. It's an enhanced version of AFL, which integrates many of the new fuzzing techniques, the new fuzzing ideas that have been presented in the literature over the past couple of years. What we did with KLEE is we limited its memory usage to 3 GB of RAM. We use no initial seed corpus. We disabled the use of dictionary, and we ran the experiment for 12 hours. So this is one of the figures that we have about the results. So this figure shows AFL++ in blue and KLEE in green for the libxml target. As you can see, it's pretty obvious from the graph that AFL visits around 3 times more code than KLEE. Here's another plot for the zlib target. On this target, AFL++ is around 30% better than KLEE. On libjpeg, AFL++ and KLEE have similar performance. They both visit around, a little bit over 1,000 lines of code. And we have this target, WORF2, where KLEE performs a lot better. It turns out that AFL++ remains stuck, early in the program and can only visit around 80 lines of code. And I think this is a good example where symbolic execution really helps when you have early constraints that the fuzzer cannot satisfy. So the takeaway about the first experiment is as follows. In general, AFL++ tends to visit more code than KLEE. If you look at the individual lines that are covered by AFL++ and KLEE, you'll see that AFL++ always visits all the lines that KLEE visits. So in that sense, in general, AFL++ is better. On one target, we saw that KLEE performs better. And something we noticed, which is pretty obvious in retrospect, is that KLEE is more consistent, meaning that it has less variance across runs. And that's kind of understandable because fuzzers use a random mutation, which is a source of non-determinism. So you have greater variance, and you might be lucky on a run and very unlucky on a different run. So let's move on to the next experiment. This is the exact same setup as the previous experiment, and we changed only one configuration. We enabled a seed corpus. We gave the fuzzer and KLEE an initial set of files as input. So if you recall from the previous slides, I don't think you do because I don't either, AFL++ and KLEE performed similarly on the libjpeg target. This plot also shows you the libjpeg target for when we enabled seeds. So what you can see that AFL++ improves significantly from 1,000 lines of code all the way to 3,000 lines of code, depicted in blue on the slide. KLEE, however, doesn't seem to improve. I don't have really time to show all the other figures, but the takeaway message of this second experiment is that AFL++ seems to be better at using seeds to improve coverage. Seeds seems to have very little impact on KLEE's performance. In fact, I have some figures to show this in more detail. So this plot shows KLEE run with seeds in the green color, and without seeds with the blue color on the zlib target. As you can see, the results are pretty similar. This next plot is for the libxml target. And interestingly, if you look carefully, you'll see that KLEE actually performs slightly better when you don't have seeds, which is depicted in blue. And I think that's kind of counterintuitive. But it might just be due to the fact that this experiment was just run for 12 hours. So going forward, I think there's one big blocker that needs to be fixed before industry can really embrace symbolic execution. And I kind of hinted about the problem earlier in the slides, and I think it's around tooling, better support for assembly code, unsupported instructions, and so on and so forth. I think today fuzzers are so easy to use out of the box that they are just the tool of choice for many of us in industry. Our results show that even though KLEE helped when no seeds were available, AFL++ in general visited more code on most programs. And I suspect that that's mostly due to state explosion. As soon as there's a loop encountered in the program, it kind of starves the state exploration. But I haven't really looked into it more in detail. But despite this problem, I still think that symbolic execution has a role to play in industry. So let me give you some context. I talked earlier about OSS fuzz, and using OSS fuzz, we run fuzzing campaigns 24/7 every day of the year. Yet what we see that after 24 hours, there's little improvements. Fuzzers do not cover new code. They don't find new bugs. So we're essentially wasting resources. And I think there's plenty of room for more expensive, resource-hungry techniques like symbolic execution. For example, instead of symbolically executing an entire program, we could just focus symbolic exploration on a smaller portion of the code, where fuzzers cannot go because the constraints are too difficult to synthesize. And I think this may help reduce state explosion while still taking advantage of SMTP solvers. I think there's already work in this direction, which is very promising, such as concolic execution and techniques like the one presented in the KLEE paper. So to conclude, I just want to say that at Google, we would really like to help the fuzzing and symbolic execution community. We started with OSS Fuzz and FuzzBench, and those services are available for you to use for free. We also have funding for research and for developers who would like to integrate their techniques into FuzzBench. More importantly, we'd love to hear what else we can do to help, so please don't hesitate to reach out and bug me. And that's the end of my presentation. If you have any question, go ahead.